So what we are going to be talking about today is the concept of nodal analysis. Nodal analysis is a very powerful circuit analysis tool that lets us use multiple applications of Kirchhoff's current law to determine unknown voltages in a circuit simultaneously. So I'm going to present this to you as an algorithm, a series of steps. And if you follow these steps in the order that I tell you to do them, and you apply the analysis correctly, you will get the correct answer every time, okay? So the first step of the nodal analysis technique is to identify nodes. So the circuit that we are going to analyze is this guy here. This is what we're going to start with. We have a 15 ohm resistor. A 5 ohm resistor. A 20 ohm resistor. A 10 ohm resistor. A 2 amp independent source. And then I'm also going to include a dependent source. 0.5 Vx dependent current source, direction down, which means I need to identify my voltage Vx. And so in this case, our voltage Vx will be the voltage drop over the 15 ohm resistor, positive polarity on the right, negative polarity on the left. Okay, so this is our circuit that we are going to analyze, and we're going to identify nodes just like we've done it previously. I like to use different colors and all that kind of stuff. So that's exactly what I'm going to do. I'm going to say the node, I have a node here on the left-hand side of my circuit. I have a node over here on the right-hand side of my circuit. I have a node here in the middle of my circuit. And I have a node here at the bottom of my circuit. So that's step one. Simply identify the nodes of our circuit of interest. I feel very strongly that all of you are capable of doing that part of our analysis. So we're off to a good start, okay? Step two is going to be to identify a reference node, or really not identify one so much so as select one. And we have the choice of which node is going to be considered our reference. So let's talk about the concept of a reference node. Okay? Our reference node, all that means is that we are going to assume that that particular node has a voltage of 0. So it serves as a reference to the rest of our circuit. Okay? So how I prefer to choose my reference nodes is usually I choose the node that has the largest number of elements connected to it, okay? When we start dealing with circuits that have voltage sources in it, I will modify how I choose my reference node slightly. But for this circuit that doesn't have any reference node, my green node is connected to 3 elements, my blue node is connected to 3 elements, my red node is connected to 3 elements, and my pink node is connected to 3 elements. So all of them are an appropriate choice for a reference node. So David, which one do you want to work with as our reference? Bottom one in pink. Okay. So we will designate our reference node by applying the ground symbol at that node. And so this means that there is 0 volts at this node. Okay. Now, it doesn't matter if that's actually true or not. We're just assuming that it is, and we're going to find out everything else with that as our reference. So everything else will be calculated with respect to that one being 0. What's interesting though is that if we have a voltage like Vx up the top that's labeled as a voltage drop over a resistor, it literally doesn't matter which node we choose as our reference and what nodal voltages we find, which I'll talk about in a moment. Vx isn't going to change, while the voltages with respect to our reference might change depending on how we analyze the circuit. So that's why it's a really powerful tool. It'll work for any circuit. We just have to know how to use it correctly. Okay? So our next step is to assign nodal voltages. So I'm going to assign them first, and then I'm going to explain what a nodal voltage is, okay? So effectively, for every node that isn't my ground or my reference, it just gets a value. So I'm going to call the node over here in green as node A, and so it's going to have a nodal voltage VA. I'm going to call this guy in the middle node B, and so it'll get a nodal voltage VB. And I'll call this guy over here to the right node C, and so it'll get a nodal voltage VC. These nodal voltages are just a shorthand notation for a voltage. And so what I mean by that is for a nodal voltage, where we have the label counts as the positive polarity terminal and ground is our negative polarity terminal. So VA is this, the voltage drop over the 6 ohm resistor, where the positive polarity terminal is at node A and the negative polarity terminal is at ground. VB is just a shorthand notation for this guy, where the positive polarity terminal is at that middle node, and again, the negative polarity terminal is at ground. And VC is a shorthand notation for the voltage drop over my dependent current source, where again, the positive polarity terminal is at node C, and the negative polarity terminal is at ground. I'm not going to actually write this plus VA minus, plus VB minus, plus VC minus, and all that kind of stuff because it's redundant. I don't need that information. I'm just trying to explain to you what those nodal voltages mean. So if it's okay, I'm going to erase those guys because things are getting a little busy. All right, so we are complete with our kind of setting things up. Now we're going to get into the circuit analysis portion of nodal analysis. So my next step, number 4, is going to be write equations for controlling variables in terms of my nodal voltages. So what I mean by this, I have a dependent source. The current that flows through that dependent source is controlled by the voltage drop Vx, which is the voltage drop over that 15 ohm resistor at the top. So I want to express Vx in terms of my nodal voltages. So how I do that is I simply take the nodal voltage present at the positive polarity terminal of Vx, which is what? Vc. So I'll have Vx is equal to the nodal voltage present at the positive polarity terminal minus the nodal voltage present at the negative polarity terminal, which is what? Va. So Vx is simply Vc minus Va. Some of you may be thinking, well, am I supposed to divide that by 15 ohms? The answer is no, okay? Vc is a voltage, Va is a voltage, Vx is a voltage. If I divided the quantity Vc minus Va by 15 ohms, that would give me the current flowing from node C to node A through that 15 ohm resistor, which is not what I'm interested in, okay? That's a very, very common mistake. People try to write these controlling equations and stuff like that and accidentally give current expressions when we're expecting voltages, okay? So anytime I want a voltage, it should just be some algebraic combination of voltages. I shouldn't divide by any resistor values or anything like that, okay? So I just wanted to be clear about that. All right, so are you all still with me? Is anything seeming wildly difficult or anything yet? I hope not, all right? Our next step is going to be to write KCL equations at all non-reference nodes. So for this particular circuit, I have 3 nodes that aren't my reference, right? Node A, node B, and node C. And so I'm going to write an equation, a KCL equation at each of those nodes, where I am going to adopt the convention that all of the currents that are leaving the node are positive, okay? The reason why I use that particular convention is it means every time, if I'm doing KCL at node A, all of my VAs will be positive and all of my other nodal voltages will get a negative sign. When I do KCL at VB, all of my VBs will be positive and all of my other nodal voltages will get negative signs. So it's just minimizing the number of negative signs that we're going to have, right? So for node A, I'm going to add this current flowing down through the 10 ohm resistor, this current flowing to the right through the 5 ohm resistor, and this current flowing up through the 15 ohm resistor. I'm going to add them together, set it equal to 0. So KCL at node A, my equation should look like this, all right? So the current flowing down through the 10 ohm resistor is just the voltage drop over the 10 ohm resistor divided by the resistor value, according to Ohm's law, right? The voltage drop is VA, the node where the current's starting from, minus 0, the node the current is flowing to, and then I divide that by my resistor value. So in this case, it's going to be VA minus 0 divided by 10 ohms. Then I'm going to take care of my current flowing to the right. So my current starts at node A, It ends at node B. So the total voltage drop is VA minus VB. And then I divide it by my 5 ohm resistor. And then my current flowing up will be VA minus VC divided by my 15 ohm resistor. Let me scroll down, try to get both of these things in the picture at the same time. Doesn't quite look like I can get all of it. Do any of you guys have literally any questions at all about how I wrote that equation? So simply the application of Ohm's law to get the individual currents flowing through those resistors. And then I add them all together and set them equal to 0 because I'm applying KCL at that node. Henry. That 10 ohm resistor right there. That's a 10. Sorry, I wrote it larger so that perhaps it looks more like a 10 than a 6. But yeah, it's supposed to be a 10. Any other questions other than my terrible penmanship? All right. So we'll now write a KCL equation at node B. So that equation will be me adding this current flowing to the left through the 5 ohm resistor, plus this current flowing down through the independent current source, plus this current flowing to the right through the 20 ohm resistor. I just add those guys together and set them equal to 0. So, Skylar, could you help me with my KCL at node B equation, please, now? VB minus VA over 5 ohms, so that's the current flowing to the left, minus 2 amps, so we get a negative sign because the current we're looking for is opposite direction, opposite the direction that the current source is supplying. And what's my third term, please? Set it equals 0. Anybody have any questions, comments, or concerns about where that equation came from? All right. Now we'll write our KCL at node C equation. Henry, you care to help me out? So let's be explicit about what I'm trying to get here. I want this current to the left flowing through the 20 ohm resistor, this current down through the dependent source, and this current up through the 15 ohm resistor. So you tell me what those are in whatever order suits you. I'm sorry, what's that? So all of our currents are originating at node C, and then for the 15 ohm resistor, it's terminating at node A. No, we're using nodal voltages. So we're using VA, VB, and VC. The only place that VX should show up in these equations that we're writing right now is for our dependent sources. And then we'll do a substitution there later. So all of our nodes, like all of our voltage drops and all that kind of stuff, in this case should be, nodal voltage, blah, minus nodal voltage, yada, or whatever. All right. So what's it going to be? VC minus VB over 20. All right, fully on board with that. So that's the current flowing to the left through the 20 ohm resistor. Plus 0.5 Vx. Okay, so that's the current flowing down through the dependent source. So all we have left is the current flowing up through that 15 ohm resistor. Over 15. Yep. VC minus VA over 15 ohms. All right. So we have four equations, four unknowns, but we could easily substitute our Vx relationship, Vx is equal to VC minus VA, into our KCL at node C equation and get this down to a three equation, three unknown system. Fantastic question. Let me scroll up here. 0.5 Vx is a current because that is a current source. It is a voltage controlled current source. I can tell that it is a current source because there's an arrow. If it were a voltage controlled voltage source, that diamond would have a plus and a minus in it. Okay. All right. So if I substitute, let's call this guy right here, equation 1, that original equation that I wrote. Let's call this guy 2, this guy 3, and this guy 4. If I substitute 1 into 4, I would get VC minus VB over 20 ohms plus 0.5 VC minus VA plus VC minus VA over 15 ohms is equal to 0. And let's use 2, 3, and 5, three equations, three unknowns, to solve this system, okay? So if we were doing this by hand, which we are not going to do, but if we were doing this by hand, we would need to simplify these and figure out what the lowest common denominator of all of our fractions is and do a bunch of hippie multiplication and boring stuff that is just ripe for opportunities for us to make a simple calculation error. Our calculators are good enough to where they can take care of all these nasty fractions and all that kind of stuff. But we have to know how to input the correct things, right? So for instance, the coefficient for VA, effectively we're doing a matrix here. We're not actually going to use the matrix. I'm just trying to illustrate what you're putting in your calculator here. So what should the coefficient for VA be? 1/5 plus 1/15. Everything that gets multiplied by a VA needs to be all added together, right? So we'd have 1/10 plus 1/5 plus 1/15 as our coefficient for VA. Our coefficient for VB would be what? Negative 1/5. And our coefficient for VC would be negative 1/15, right? This is going to be multiplied by VA, VB, and VC. And this is going to be equal to some constant term, which in our case, our constant is simply 0. If we look at equation number 3, what is our coefficient for VA? -1/5. What is our coefficient for VB? 1/5 plus 1/20. And our coefficient for VC, -1/20. And our constant value term, so we need to move that to the right-hand side of the equal sign. So it's that 2 amp term. When we move it over, it gives us positive 2 amps. So this will be +2. Let's look at equation 5. So our coefficient for VA is going to be what? Yeah, so -1/2 plus -1/15. Our coefficient for VB. Jessica, got any thoughts? Coefficient for VB in equation number 5. Pardon? No, so there's a V, it's only going to be 0 if there's no VB, but there's a VB in that first term, right? Problem. Exactly right, -1/20. And then our coefficient for VC is going to be what? So 1/20 plus 0.5 plus 1/15, right? Because VC shows up 3 times, so it should be the sum of 3 coefficients. Forgot 1/20 plus 0.5. It's 1/15. Yeah, there we go. So, and this is going to be equal to 0 because there's no constant term. So these are the coefficients that you'll enter into your calculator. You can literally put it in as just the sum of fractions, and your calculator will handle all the conversions and all that kind of stuff that it needs to do, okay? So we don't need to actually write this part down once we get comfortable looking at the equations and just typing that stuff in. I'm just doing it now so that you have something to refer back to if you don't get the same answer that I do. So let's take a couple of minutes and use our numerical solvers on our calculator, our system solvers on our calculator, and figure out what value VA, VB, and VC should have. Bradley. Where the 2 came from? Sure. So if we look back at equation 2, right, so there's -2 amps, but when we move it to the other side of the equal sign, so we should have variables on the left-hand side of the equal sign, constant terms on the right-hand side. So when we move that -2 from the left-hand side of the equal sign to the right-hand side of the equal sign, that's where the +2 came from. If there's any know how to use the system solver on their calculator, I would be happy to come by and at least show you where it is and all that kind of good stuff. I know for sure where it is on a TI-36. I'm pretty sure I know where it is on a Casio 115, and I have a pretty good idea of where it is for the 991. Yeah, simultaneous. And then we have 3 and so these guys are here. So X y is press over. That's our constant. Jessica, were you raising your hand? I'm sorry if I neglected you. All right, so 5 for All right, so by all means, continue working with your calculators. I'm just showing you these values which are correct. So that if you put stuff in correctly, you should get those guys. And if you put stuff in incorrectly, then obviously you won't get those guys. If anybody needs help using their calculator, I'm happy to explain what to do. All right. How many of you were able to do this correctly? Roughly half of you. How many of you got it incorrect? Okay, that works for me. I don't think for me. And how many of you didn't finish? The reason why I asked about not finishing is because you're going to be asked to do this type of analysis where you're setting up a system of equations and then solving said system multiple times on your exam. So you need to get in the habit of doing this, entering a system like this into your calculator efficiently and correctly if you want to, finish the exam. So while MathCAD and online computer algebra tools like Wolfram Alpha and things like that can absolutely be used to solve these systems, I would argue that any 3x3 system, so 3 equation, 3 unknown system or smaller, you should use that as an opportunity to practice putting these in your calculator in a relatively quick amount of time. Bradley.
Okay, I wanted to ask, what's like the largest amount of variables in this equation? Like it says three by three, what's like the biggest time frame of that? You can expect to run?
Fantastic question, okay? So what Bradley asked was, what's the largest system of equations that I could ask you all to solve on your exam? A 3 by 3 system. Now, let me say that with a caveat, okay? It may look like it's going to be a 4 by 4 system or something larger. And the expectation there would be that you could do some sort of circuit simplification to bring it down to a 3 by 3 system, which you could then solve, okay? Now, I believe I mentioned this on the first day of class. The TI-36X, which is my personal favorite, can solve 3 equation, 3 unknown system. The Casio FX115 can solve a 3 equation, 3 unknown system. The Casio FX991, which is about, I think, $4 to $5 more expensive than the 115, can solve 4 equation, 4 unknown systems. It is the most powerful calculator that is NCEES approved. So while it is not my personal favorite, and it's not my favorite because I find the TI easier to do complex calculations on, for this kind of stuff, for the DC circuit analysis, it's probably the best calculator you can buy, and it's about 20 bucks. Some of you still have TI-30Xs, and you're going to find that is it's going to be lacking for what you're going to be asked to do on exams in this class. So while I am probably as much of a TI fanboy as anybody you've ever met, those calculators just don't have the power to do what we need them to do for this class. So they were perfectly reasonable for your engineering 120 class. It's just going to slow you down in this class. So I would invest the extra money in getting a slightly better calculator. Nick. All right, so the negative 0.5 is coming from this 0.5 right here and a factor of -1 in front of the VA. So when I multiply those two guys together, I get -1/2. Right, so the bottom left-hand corner of the matrix is the coefficient for VA in equation 5. So I should have, there's a 0.5 times negative VA, so that's that negative 0.5. And then there's also this -1/15 from here. So to be clear here, this column here is all my coefficients for VA. The middle is all the coefficients of VB, and the rightmost, all the coefficients of VC. And then these are all my constant values, which I'm just going to call capital C. So that's what your calculator is doing, is solving this matrix, and you are inputting it so that it looks pretty much like this as well. I think that's the graphical user interface for most of the calculators that I've observed. I don't know how the HP calculators that are NCEES approved do it, because I've never actually seen one of you guys use one. So, but the TIs and the Casios look like this, so I teach it to you like this. All right, so I think we've spent enough time on this particular example problem because we're about 45 minutes into class at this point. So let's mess things up by adding voltage sources. Okay. So we're going to work a simple problem with a voltage source first, or voltage source or two first. So our second circuit is going to be something like this, where let's say that we have 12 ohm resistor, a 8 ohm resistor, a 3 amp source, a 5-volt source, and a 20 ohm resistor. So we are going to just use the simple steps that we discussed earlier until things break down here. Okay, we're going to see that they'll break down pretty quickly, and then we'll talk about how to overcome the issue. So what should my first step be? Identify my nodes. That is not how you spell nodes. So let me break out my colored markers. So that's one node. That's another. That's another. That's another. Which one, Abby, which one do you want to be the reference node? All right. So this guy, is that not, to me, that looks pink. Okay, the bottom one. Okay, I'm sorry. I'm a simple man, so colors get me. Yeah. Okay, well, all right, so the bottom node. All right, I'm okay with that. All right, thank you, and sorry for the confusion. So we have those 3 nodes on the top. So let's just label them VA, VB, and VC again. So that's step 2. Oh, actually, step 2 was select our reference node. My apologies. Step 3 is assign nodal voltages. So VA, VB, and VC. Everybody okay with that? Step 4 is controlling variable equations. We don't have a dependent source, so we don't need to do anything for that. And then step 5 is KCL at non-reference nodes. So we are going to wind up erasing this as step 5 in just a moment, just to let you know. All right. So Kennedy, how do I write my KCL equation at node A? Thank you, ma'am. Wonderful job. Normally, I would make one of you guys suffer and ask you to write my KCL equation for node B, but I'm going to do it this time to explicitly tell you where it falls apart, okay? So we can get the current flowing to the left through the 8 ohm resistor rather easily, right? That's going to be VB minus VA over 8. We can get the current flowing down through the independent current source rather easily. That's just going to be -3 amps. But then we run into this guy. Current flowing to the right through my voltage source. So this is an independent voltage source, which means the voltage drop over it is fixed at 5 volts, and the amount of current flowing through it is whatever the hell it needs to be to make the circuit work. There is no way that we can relate the current flowing through that 5-volt source from left to right in terms of our nodal voltages. The best thing that we could do is just call it, you know, VS left to right or something like that. Okay. So I'm going to just label this guy IVS left to right. Set this equal to 0. Okay. Now, I'm going to try to write a KCL equation at node C. So I'll have my current flowing down through my 20 ohm resistor. So that's easily VC divided by 20 ohms. And then I have another current flowing through a voltage source. So let's call this guy IVS RL for the current flowing through the voltage source from right to left. So how many equations do I have? Carter, what's your question?
Is IVS LR not the negative IVS RL?
It absolutely is. We'll get to that in just a moment. You're 100% correct. Those are the exact same currents flowing in opposite directions. And recognizing that is a key to what we were about to do. Presently, we have 3 equations and 5 unknown quantities. Okay. So what I'm about to do is I'm going to form what's called a supernode. Okay. A supernode is just going to be a combination of nodes. And I'm going to denote that by just putting a loop around things, okay? So my supernode, anytime I have a voltage source, I am going to have a supernode. So I'm just going to put a dashed loop around this guy, okay? And I am going to treat this as a single node when I write my KCL equations, meaning I'm going to add up all of the currents that flow out of my supernode and set them equal to 0. Let me explain why I can do that. So if I write an equation that sums all of the currents flowing out of my supernode, what I'm doing is I'm just adding my KCL at node B equation to my KCL at node C equation, okay? All that is saying 0 plus 0 is equal to 0, which has to be true. What it does is say that the current flowing from left to right through my voltage source is canceled out by the current flowing right to left through my voltage source, which is what Carter just noticed, right? So effectively, I can avoid writing a current that flows through my voltage source because they're just going to cancel each other out when they go in both directions, okay? So my supernode equation is going to be adding this current plus this current plus this current together and ignoring my voltage source entirely, all right? So let's scratch this guy out, scratch this guy out, and I'm moving this guy down. It's going to be step 6, but we're going to go ahead and take care of it now. So we're going to write our KCL equations at all nodes and supernodes that do not contain our reference, which in this case, our supernode doesn't contain our reference, so we're going to get that equation. So KCL at supernode, and I'm going to call this supernode B, C, because it contains nodes B and C, and write a KCL equation, right? So the current flowing to the left through my 8 ohm resistor is going to be what, Michael? The current flowing to the left through the 8 ohm resistor. Kai, help him out. Okay, so you're close, but you're doing a little more than you need to, okay? So when we're adding these two nodes together, we don't say that it's going to be VB plus VC. We do the exact same thing that we did, okay? So it'll just be VB minus VA over the 8 ohms, all right? So we are combining the nodes to apply KCL, but that's the only way that we're combining it. It's just multiple paths to do KCL on. So we're going to have VB minus VA over 8 ohms. What's the current down through the independent current source going to be, Norman? -3 amps. And then Avery, what's the current down through the 20 ohm resistor? EC over 20, that's it. Set it equal to 0. So notice that is literally the KCL equation we wrote at node B and the KCL equation we wrote at node C combined together with those voltage source currents going away because they cancel each other out. That's all we're doing. Okay. So this brings up a slight problem. We now have, so we went from 3 equations with 5 unknowns to 2 equations with 3 unknowns. So we're in a little bit better position, but we still need to figure out where that last equation is going to come from, okay? Anytime we have a voltage source, we will have a voltage relationship equation. Okay, so that's going to be step 5. Voltage equation for all supernodes. Every time we have a voltage source, we have a supernode. And every voltage source is going to get a voltage relationship equation, okay? So let me talk about this voltage relationship equation. We have a voltage source here in this circuit. How much voltage is provided by it? 5 volts. So here's our voltage relationship equation. Five volts, which is the voltage provided by our source, will be equal to the nodal voltage at the positive polarity terminal, which is what? VB, minus the nodal voltage present at the negative polarity terminal, which is VC. So we write our voltage relationship equation in the exact same way that we write any other voltage when we do nodal analysis. Voltage is always positive polarity, or nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. Always, always, always. We now have 3 equations, 3 unknowns. We can throw it into our system solver on our calculator. and get some sort of result. So take the next couple of minutes and do just that, please. So let me know when most of you have gotten the same answers that I have here, which I fully believe to be correct. All right, so hopefully you all have been able to set up this system in your calculators, solve it, and get these values for VA, VB, and VC. And thus, I believe that I have demonstrated that we can use nodal analysis to solve for unknown voltages in really any circuit we care to analyze with it, okay? Now, let's talk about how powerful knowing all the voltages is. Using this particular problem, what if we wanted to determine the power supplied by the 3 amp source? Okay. So let's put that in red here. P 3 amp supply. How could we determine that using the nodal voltages that we've determined. So if I want the power supplied by a source, what do I need to know? The voltage drop across the source and the current flowing through the source. Well, the current flowing through this current source is pretty trivial. It's 3 amps, right? So what we need for power supplied is for the current to be flowing into the negative polarity terminal and out of the positive polarity terminal, right? So we are looking for, let me erase these guys because we don't need them anymore. They're kind of getting in the way as well. We're looking for this voltage, VCS, where the current is flowing into the negative polarity terminal, because that will give us the product of the current and that voltage will give us the power. Well, how do we get VCS in terms of our nodal voltages? I think I heard it, but I maybe just wanted to hear it. So if somebody said something, speak up. Equal to VB, absolutely right. The voltage drop over our current source is the exact same thing as that nodal voltage VB, because they're both defined to be the potential difference between that orange node and ground, right? So the power absorbed by our current source, E CS, did I say CS or VS? Oh, I called it 3 amps. Okay, so P 3 amps supplied is simply VB times 3 amps, which is 97.5 watts. What if I wanted the power absorbed by the 8 ohm resistor? So if I want the power absorbed by a resistor, I can either do the product of the voltage drop across the resistor and the current flowing through the resistor, or I can do the voltage drop across the resistor squared divided by the resistor value, or I can do the current flowing through the resistor squared multiplied by the resistor value, right? So when we're dealing with nodal voltages, that second option, the voltage drop squared divided by the resistor value, is probably the easiest. So what's the voltage drop? Oh, sorry, Bradley. Oh, we're absolutely gonna do that in just a moment. Yep, that's the next thing I'm gonna do. Yes, so let's take care of this resistor first here real quick, right? So the voltage drop over the resistor, the 8 ohm resistor, what's that gonna be in terms of my nodal voltages? VB minus VA or VA minus VB, I don't care, I'm squaring it when I get the power, right? So we don't really care which polarity we have when we're doing a power calculation for the voltage drop across a resistor. So P 8 ohms is VA minus VB squared divided by 8 ohms, which is going to be identical to VB minus VA quantity squared over 8 ohms. Which looks like 21.125 watts of power absorbed. Okay, so everybody okay with this? All right, so Bradley asked what I was intending to ask you guys anyway, which is determining the power supplied or absorbed by our voltage source. So which one do you guys want to do? The absorbed power or the supplied power? Absorbed. Okay. So the power absorbed by our voltage source, let's call that P 5 volt absorbed. And so to get the power absorbed by the voltage source, we need to know the voltage drop over it and the current flowing through it. and we want the current flowing through the positive polarity terminal, right? So we have two options for that current, okay? So I would argue that this current right here is the current that flows into the positive polarity terminal. Or we could add this guy and this guy together because they combine and flow into the positive polarity terminal. So either one of those options should give us an identical answer. So from that, P 5 volt absorbed is going to be our 5 volts from our voltage source multiplied by VC over, what size resistor was that, 20? Yeah. Which will be exactly identical to 5 volts multiplied by VA minus VB over 8. Plus that current source, which I believe was 3 amps. So take a moment, throw these guys into your calculator, and make sure that the answers are the same, because if they aren't, something's broken. So in both cases, I get positive 6.875. All right, so nodal analysis can be used not only to determine unknown voltages in a system, but we can then use those now known voltages to determine any voltage, so the voltage drop across any circuit element, the current flowing through any circuit element, and the power absorbed or supplied by any circuit element. So nodal analysis is a very, very powerful tool. Bradley.
I just wanted to ask you, like, how will we find the power supply?
So the power supplied by that voltage source just means we want the current flowing in the opposite direction.
Will it be negative?
So we could have negative VC over 20, or we could have VB minus VA over 8 plus negative 3. Yeah, literally just change the directions on the arrows, and there we go. And that's just from using the passive sign convention. All righty, so that's enough out of me for today. You have an in-class assignment that is, I believe, 3 problems long. Maybe it's only 2, I don't remember. It's been a minute. Take the next 40 minutes roughly and have a crack at it, and I'll be here to help if you have any questions.